The internet glance is so far away that it is catching light that has already been voyaging for over 13 billion years. Yet the universe has been extending, and thus, the light has been extending as well. The majority of distant worlds we recall are close to the time of the Big Bang. The immensity of the universe might seem vast, but every last bit of it started from what we allude to as the singularity. Currently, this operates in a manner that applies to the Big Bang theory's interpretation. Anyway, the James Webb Space Telescope, JWST, has revealed significant mysteries about the birth and development of the universe, leaving us dumbfounded. Prestigious physicist Brian Cox has proclaimed that the noteworthy discoveries of the JWST might actually alter our perception of the entire universe. Join us as we delve into these brand new discoveries about the heavens that promise to alter our understanding. The James Webb Space Telescope, named after the well-known NASA executive James E. Webb, remains a wonder in galactic investigation currently underway. This telescope represents a huge mechanical leap forward from its ancestor, the Hubble Space Telescope. Because of a collaboration between the American Space Agency NASA and the Canadian Space Agency, the JWST surpasses the abilities of its predecessor. It utilizes cutting-edge design and technology optimized for focusing on the universe in incredibly fine detail. Unlike the Hubble, the JWST conveys clear and sharp pictures of far-off heavenly bodies, primarily operating in the infrared range. This interesting component permits it to infiltrate astronomical residue and locate items of the divine that were previously hidden from our view. With its enormous primary mirror measuring 6.5 meters, made out of 18 hexagonal sections, the JWST reduces Hubble's reflector size. Weighing approximately 1.5 million kilograms, it orbits the Sun at the second Lagrange point, L2, away from Earth. This location ensures a steady and continuous view of the universe. While looking into the far-off corners of the universe requires years of investigation, it also includes a type of time travel. The JWST uses infrared instruments to observe heavenly objects and occurrences that date back billions of years. Due to the expanding universe, the light from these objects shifts toward the red end of the spectrum, redshift, moving from the visible range to the infrared frequency. More importantly, the JWST can identify this infrared light from celestial bodies at extreme distances, empowering researchers to investigate the onset of stars, explore cosmic system development, and examine exoplanet atmospheres. Its latest historic discovery involves locating an unfathomable mass of cosmic systems at the very edge of the observable universe. This finding casts doubt on the veracity of our current understanding of cosmic formation, provoking a reassessment of key cosmological assumptions. To better understand how we got to this point, we should take a short excursion through the history of space investigation. Early civilizations like the Greeks and Chinese laid the foundation for understanding planetary movement by observing divine bodies. In the 17th century, Newton's laws provided a theoretical framework for space travel. In the mid-20th century, Edwin Hubble, an influential astronomer, made historic revelations in cosmology and observational space science. His observations uncovered that far-off nebulae were distant, isolated galaxies beyond the Milky Way, changing our understanding of the universe's size and expansion. Hubble's law established that galaxies farther away were moving away at higher rates, providing proof of the universe's expansion. Space exploration during World War II marked the beginning of the space race. The Soviet Union's launch of Sputnik in 1957 became the first artificial satellite in orbit. Yuri Gagarin's orbital trip in 1961 and the Apollo 11 moon landing in 1969 were crucial accomplishments. Fast forward to 1990, when the Hubble Space Telescope was launched, providing exceptional clarity and stunning insights into the universe. The journey from ancient observations to the technological marvels of the James Webb Space Telescope showcases the constant improvement in our ability to interpret the universe. The Hubble Space Telescope, HST, for instance, captured the well-known Pillars of Creation image in the Eagle Nebula, revealing a star nursery formed by massive columns of gas and dust. Another significant accomplishment was the Hubble Deep Field, capturing thousands of galaxies in what appeared to be a void patch of space. The HST also identified the atmospheres of exoplanets, detecting organic and water-based molecules in distant worlds, hinting at the possibility of habitable zones beyond our solar system. Its observations of the closest observed supernova, SN 1987A, shed light on the life cycle of massive stars. These successes established the Hubble Space Telescope's legacy as the foundation of modern cosmology. However, its replacement, the James Webb Space Telescope, was designed to elaborate on technological advancements and lessons learned, providing a more detailed model of our comprehension of the universe's origins. According to our current understanding, around 13.8 billion years ago, the universe began as a scorching and dense singularity. Rapid expansion gave rise to matter, energy, and fundamental forces. As the universe grew, it cooled, resulting in the formation of atoms, stars, galaxies, and the various structures observed today. The Big Bang Theory also explains cosmic microwave background radiation, the abundance of light elements, and the large-scale structure of the universe. Despite being a widely accepted theory, the Big Bang initially faced doubts and challenges. Alternative models, like the steady-state theory, suggested a universe without a specific beginning. Concerns about evidence supporting the initial singularity, expansion, and observed anomalies arose. Most of these objections were addressed over time. A significant piece of evidence came in 1965 with the discovery of cosmic microwave background radiation, aligning with Big Bang predictions. Space missions like WMAP and COBE, along with technological advancements, further strengthened the theory. Accurate measurements of cosmic microwave background radiation were remarkably well suited to theoretical forecasts. Enter the James Webb Space Telescope. With advanced infrared instruments capable of looking through cosmic dust, it primarily operates in the infrared range. This allows it to capture the universe's earliest light and observe objects formed shortly after the Big Bang. Its infrared capabilities enable it to concentrate on star-forming regions, celestial nurseries, and hidden cosmic structures that optical telescopes cannot detect. Infrared light, with longer wavelengths compared to visible light, can penetrate dust from other stars, overcoming one of the Hubble Space Telescope's limitations. The JWST can also observe cooler objects that emit mainly in infrared, making it ideal for studying phenomena like brown dwarfs, exoplanets, and distant galaxies. As celestial bodies move away, their emitted light waves get stretched, causing a shift toward longer wavelengths, redshift. The JWST's infrared capabilities allow it to detect these redshifted signals, capturing light from the early universe and providing information about energetic occurrences during its formation and evolution, such as merging black holes or the births of new stars. The JWST's ability to peer into the distant past is revolutionizing our understanding of cosmic evolution. By capturing light that has traveled for billions of years, it allows scientists to witness the universe as it was shortly after the Big Bang. Its advanced instruments, such as the Near-Infrared Camera and IR-CAM, Mid-Infrared Instrument, MIRI, and Near-Infrared Spectrograph, and IR-SPEC, enable detailed observations of faint and distant objects, unlocking secrets that were previously inaccessible. One of the JWST's most remarkable achievements is its capacity to study exoplanets in unprecedented detail. By analyzing the infrared light passing through an exoplanet's atmosphere, scientists can identify the chemical composition of these distant worlds. This technique, known as transmission spectroscopy, can detect water vapor, carbon dioxide, methane, and other molecules that are essential for life as we know it. Recent observations have already revealed the presence of water vapor in the atmosphere of several exoplanets, raising the possibility of habitable environments beyond our solar system. Moreover, the JWST is shedding light on the formation and evolution of galaxies. By observing galaxies from different epochs, it helps scientists piece together the cosmic timeline, from the earliest proto-galaxies to the vast galaxy clusters we see today. The telescope's sensitivity to infrared light allows it to detect faint, distant galaxies whose light has been stretched by the expansion of the universe. This capability has led to the discovery of galaxies that formed just a few 100 million years after the Big Bang, challenging existing models of galaxy formation and prompting scientists to refine their theories. In addition to studying distant galaxies, the JWST is also exploring the life cycles of stars. By observing star-forming regions hidden within dense clouds of gas and dust, the telescope provides insights into the processes that give birth to stars and planetary systems. Its infrared capabilities allow it to see through these obscuring clouds, revealing the intricate structures within stellar nurseries. Recent observations of regions, such as the Orion Nebula and the Carina Nebula, have provided breathtaking images of young stars surrounded by protoplanetary disks, where planets are beginning to form. The JWST's contributions extend beyond distant galaxies and exoplanets. It is also deepening our understanding of objects within our own solar system. By observing planets, moons, asteroids, and comets in infrared light, the telescope can reveal details about their composition, surface properties, and atmospheric dynamics. Recent observations of Jupiter have captured stunning images of its turbulent atmosphere, including the Great Red Spot and polar auroras. The JWST has also studied the icy moons of Jupiter and Saturn, such as Europa and Enceladus, which are considered prime candidates for hosting microbial life due to their subsurface oceans. One of the most profound implications of the JWST's discoveries is their impact on our understanding of the fundamental laws of physics. By observing the universe's earliest light, the telescope provides a unique opportunity to test the predictions of cosmological models and explore phenomena that cannot be replicated in laboratory experiments. For example, its observations of the cosmic microwave background radiation offer insights into the conditions that prevailed shortly after the Big Bang, while its detection of gravitational waves from distant black hole mergers opens new windows into the nature of space-time itself. Despite its groundbreaking achievements, the JWST's mission is still in its early stages. Over the coming years, scientists expect to make even more profound discoveries as they continue to explore the universe's most distant and enigmatic regions. Each new observation has the potential to reshape our understanding of the cosmos, revealing unexpected phenomena that challenge existing theories and inspire new lines of inquiry. In conclusion, the James Webb Space Telescope represents a monumental leap forward in our quest to understand the universe. Its advanced infrared capabilities, combined with its unprecedented sensitivity and resolution, have already begun to revolutionize fields ranging from cosmology and astrophysics to planetary science and astrobiology. As it continues to explore the cosmos, the JWST promises to unlock new secrets about the origins, evolution, and ultimate fate of the universe, solidifying its place as one of the greatest scientific instruments of all time. Telescopes relied on visible and ultraviolet light observations, making it challenging to explore the early universe, where these wavelengths are absorbed or distorted by interstellar dust and gas. The James Webb Space Telescope, JWST, represents a significant leap forward in observing galaxies from the universe's early stages. Unlike its predecessors, the JWST can observe celestial objects that formed within a few 100 million years after the Big Bang. Using its infrared sensitivity and advanced imaging capabilities, the JWST has uncovered an abundance of ancient galaxies, offering remarkable clarity and detail in understanding the universe's evolutionary history. Preliminary results from JWST observations have stirred waves in established cosmological models. The detailed data challenges several aspects of prevailing theories, prompting cosmologists to reconsider fundamental principles governing how we understand cosmic evolution and structure. Discrepancies between observed data and theoretical predictions have sparked intense debates within the scientific community. JWST observations have revealed a larger number of galaxies in the early universe than anticipated by existing models, suggesting a more complex and rapid evolution process. Some observed early galaxies appear more developed than expected, challenging conventional models predicting slower development. The discovery of an unfathomable mass of galaxies challenges the assumed distribution and arrangement of large structures, revealing a more intricate and denser cosmic web than previously thought. These observations raise fascinating questions and avenues for further exploration. The existence of large structures challenges early models of cosmic structure formation, prompting researchers to refine models for a better explanation. Understanding how such vast structures gathered rapidly after the Big Bang presents a puzzle that requires an explanation that doesn't violate fundamental principles of cosmology. Significant disparities in the conditions of the early universe compared to predictions based on existing models have also been revealed. These differences could suggest previously unknown physical processes, unexpected conditions, or unidentified cosmic phenomena. In simple terms, these variations have prompted scientists to rethink and improve our models of the universe. Currently, all we can do is say that further exploration is required to incorporate these surprising observations into a more comprehensive understanding of the universe. Initial observations often provide exciting glimpses into the universe, but investigations sometimes reveal differences. For example, early observations may show specific properties or arrangements within distant galaxies that, upon closer examination, reveal fluctuations in their composition, structure, or evolutionary pathways. In conclusion, enormous phenomena are incredibly complex and require careful investigation for us to accurately understand their true nature. Spectroscopy, a method that helps unravel the properties and history of celestial objects, is an example. It involves analyzing the light emitted or absorbed by astronomical objects. By examining the properties of light, spectroscopy provides detailed information about the chemical composition, temperature, density, and movement of celestial bodies. This analysis helps us understand the origins, development, and contributions of celestial bodies to the cosmic tapestry. The JWST has uncovered numerous cases where initial observations differed from later investigations. For instance, initial observations of distant galaxies suggested a simple structure primarily dominated by lighter elements like hydrogen and helium, in line with theoretical expectations. However, spectroscopic analysis using the JWST showed fascinating variations in elemental signatures, identifying heavier elements or compounds previously undetected or misunderstood in the early universe. This challenges conventional ideas about the early universe's chemical composition and the mechanisms responsible for their development and dispersion across vast distances. Similarly, initial assumptions about galaxies in the early universe were based on preliminary observations, suggesting a relatively uniform pattern of development and organization. However, more detailed investigations by the JWST revealed a much more diverse and complex array of chemical compositions within these galaxies. The James Webb Space Telescope, JWST, continues to redefine our understanding of the cosmos by shedding light on previously hidden corners of the universe. One of its most exciting capabilities is its ability to study exoplanets in unprecedented detail. By analyzing the atmospheres of planets orbiting distant stars, the JWST can detect crucial chemical signatures, such as the presence of water vapor, carbon dioxide, methane, and other organic compounds. These findings provide valuable insights into the potential habitability of exoplanets and the conditions that might support life beyond Earth. In addition to exploring distant worlds, the JWST is transforming our understanding of star formation. It can observe the birth of stars in regions where young stars are surrounded by dense clouds of gas and dust, which optical telescopes cannot penetrate. With its ability to detect infrared light, the JWST captures the faintest glimmers of these new stars as they emerge from the darkness, offering a clearer picture of the processes that lead to star and planetary system formation. By studying these regions, astronomers are gaining a deeper understanding of how stars like our Sun come into existence and evolve over time. Another remarkable aspect of the JWST's research is its ability to peer into the hearts of galaxies. Black holes, particularly supermassive ones, are believed to reside at the centers of most large galaxies. JWST's advanced instruments allow scientists to observe the behavior of matter around these black holes, providing new insights into their growth, their influence on galactic evolution, and the powerful jets of energy they emit. These findings are helping astronomers piece together the story of how galaxies and their central black holes evolve together, influencing each other's growth. Moreover, the JWST's discoveries are not only answering long-standing questions, but also raising new ones. As it probes deeper into the history of the universe, it is uncovering phenomena that challenge existing theories and models. These challenges drive the scientific community to redefine current cosmological models and open up new avenues for research that were previously unimaginable. The discoveries of the JWST are not just pushing the boundaries of what we know. They're helping to reshape the fundamental principles of how we view the universe itself.